Okay, so as I have explained last time, so actually there is only one section left which we have to cover, which is the change of variables. So last time we saw already how to how the triple integral gets affected if we change to cylindrical or spherical coordinates. And I explained last time that this is the first instance of a general substitution rule for double integrals and triple integrals, which we want to establish today. So our goal is, okay, so we know from last semester if we have given an integral, then one of the techniques which proved to be very useful last semester was the substitution rule. So in some cases we can simplify integral by introducing a clever substitution. So what we do is, okay, we replace x by some u, so we have some function, some transformation which maps u onto x, and if g satisfies some assumption, then we know we can replace dx by the derivative of g times du. So this was the rule, how to memorize the substitution rule. But of course, this is just formal what I'm doing here. And if we want to apply such a substitution, what we have to do is, okay, we have to find values c and d which get mapped on. If you apply g, c and d get mapped onto a and b. And you replace then x by g of u and dx by this expression here. Okay, so this was the substitution rule. The way I use here the substitution rule is just formal. Okay, so this is what I'm doing here is just formal. But last semester I showed you how to prove this rule. And this is a good way to memorize it. Now, what we want to do today is we want to find the corresponding rule for double integrals and triple integrals. So we have now a double integral over some plane region D, f of xy dA. DA. And what we want to do is, okay, we replace this function here by a general transformation, which maps xy onto some, let's say, uv plane. So here we are in the xy plane, and like here we went from the x line to the u line. Here we want to go from the xy plane to the uv plane. So what we will have here is some substitution, some function which tells us how to map so it depends how I look at it, but okay, so let's look at it like this here. So we have some transformation which maps the uv plane onto the xy plane, and what we want to do is, okay, we want to replace the two variables x and y by the two new variables u and v. Okay, so for this we have to the first thing we have to figure out is, okay, what happens with d under this transformation, or in other words, if this is some r here, we have to figure out, okay, which plane region in the uv plane under this transformation gets mapped onto r. Okay, so this is certainly this corresponds here to finding the upper and lower limit. So we have to find some region C which under this transformation, so some region S in the uv plane which under this transformation gets mapped onto R. Then we replace x and y by our new expressions. So we have here x of uv and we have y of uv. And now here we have still to figure out, okay, what will happen here. Okay, and then our new integration is in the uv plane. Okay, I could also write here something like dA, but the meaning of dA here would be different, because here I'm in the xy plane and here I'm in the uv plane. And this transformation which I have here will map this region here, this plane region S, okay, onto this plane region R. And here you have this map here acting on the two planes here. Okay, so normally we will such a map we will function from R2 into R2, from the plane into the plane. We will call it T, a transformation. And what you see here is okay, so this is S, and under T, S gets mapped onto this region here, which is R. Okay, so you have to compare those two situations, exactly the same. Okay. So once we have established such a result, okay, we have to do exactly the same as here. So we have given our transformation, we have to figure out, okay, which plane region under this transformation gets mapped onto R. Then this plane region, okay, will determine the new boundary, the new limit of the double integral, or the new region over which I have to integrate. So this step corresponds replacing AB by CD. It was more simpler here. Then I just replace x and y by my new expressions, but we still have to figure out, okay, what will happen with the dA. We saw already instances for such a change of variable, namely, we saw already the special case where we replaced x and y by polar coordinates. So u and v then become r and theta. And in this case, okay, if we change to polar coordinates, what we have to do is, okay, we have to replace the plane region by the description of the plane region in polar coordinates. This is in the S. We have to replace x and y by the corresponding expressions for the polar coordinates. And we know, in this special situation, we know what happens with the dA, namely the dA becomes r times, and then d theta dr. Okay, but we want to now in general figure out, okay, what will happen if we apply a general transformation T, what will happen with the dA. Now, the transformations we are interested in, so-called C1, normally so-called C1 transformations. So T C1 is called C1 transformation. If the four partial derivatives, the partial derivative of x with respect to u, the partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v all exist and are continuous. Okay. So such a special transformation we will call a C1 transformation. And the functions which we are going to choose as substitutions will all be C1 transformations. Okay, so maybe it's good to look at an example. You'll find this example in our textbook. An example for a C1 transformation. So you have for instance, for such a transformation, okay, you might have the following one: x is equal to u square minus v square, and y is equal to 2uv. We should at least look at one example because actually this is a new situation for us. A function from the plane into the plane. Until now, last semester we considered functions from the real line to the real line. And this semester, we were mainly concerned with functions from the plane into the real line. And this is now a function from the plane into the plane. Now, for instance, okay, if you in the UV plane, if you have in the UV plane, let's say the rectangle, the unit rectangle, so this one. so here you have 1, and here you have also 1. Okay, so and we look at this domain here, because this is in the UV plane. Okay, so we would actually be here. Okay, if we look at this situation, so this is our S. Okay, now what is the image of S under this transformation T? Normally, if you have to figure something out like this, okay, so here you have now X and Y. Okay, and here you have the map T, mapping S onto some region here. Okay, now normally if you have to do something like this, you will easily observe if, for instance, U is fixed, or let's say if V is fixed, okay, then you see that if you have something in between, if U is between 0 and 1, okay, then here, if you look at the function, it will be in between the left point and the right point. So this will be preserved. So from this, you see that you just have to look at the boundary. Okay, you figure out what is the image of the boundary, okay, under this mapping, and then what is inside the boundary will be mapped inside of what you figure out for the boundary. Okay, so normally you just look at the boundary. What happens with the boundary? Now, for instance, if you look at this part here. Okay, so this, call it C1. Okay, so what happens with the image of this part here? Here you see V is equal to 0, so this will be equal to 0. This will be equal to 0, which means Y is equal to 0. And you see that U is between 0 and 1, so X is between 0 and 1. Okay, so as you walk from here to here you walk from 0 to 1. Okay, so this will be the image of this part here. Okay, you just have to take these expressions. You plug in Y is equal to 0. Okay, U is between 0 and 1. Y is equal to 0. V is equal to 0. This is equal to 0, so Y is equal to 0. And here you have U squared, U between 0 and 1. So you walk like this. Now, if we walk up here, okay, so this would be, let's call this C2. Okay, so on C2, you have that U is equal to 1, and V is between 0 and 1. Okay, so you just plug this into the expressions. So what do you get? From this you get that X is equal to 1 minus V squared, and Y is equal to, so U is equal to 1, 2V. Okay, so you see you can express this. You express V is equal to Y half, so X becomes 1 minus Y squared over 4. Okay, and as V goes from 0 to 1, you see that Y goes from 0 to 2. So Y from 0 to 2. Okay, so you start here, and you this is for Y, and this looks like a parabola. Okay, so if Y goes up to 2, then here you are at 0. X is equal to 0. So what you this looks like this here. Okay. Now, because of symmetry, you can easily guess that the other parts you walk down here again, and then you walk like this. Okay, so you see, in particular, for this special transformation, okay, the boundary of S gets mapped onto this boundary. Okay, so if I just consider here the boundary of S, okay, the image under T will be this curve here. And it's easy to figure out that for this special function, it's easy to see that what is inside gets mapped into what is inside here. So under this transformation, okay, S gets mapped onto R. So you see, this already shows you somehow the tricky part of substitution for double integrals. Okay, so if you encounter an integral, okay, like this here, where R is given by this here, okay, you might think about this transformation. Okay, because under this transformation, the domain gets much easier. Okay, the domain just gets this rectangle. But of course, you see that it's not so easy. Okay, because if you're given this problem, okay, some function f, it's maybe not so easy to come up with this transformation, because you have to figure out the transformation, okay, such that the region which gets mapped onto R under the transformation gets easier. Okay, it's normally not so easy to figure out the right transformation for doing this. But also the substitution rule we learned last semester. It's not always easy to find a good substitution. It's the same problem here, but here things are getting more complicated because you have here a plane region over which you integrate. Okay, and your transformation can either make R more simpler, which might lead to this integral is simpler to compute, or it might simplify f. But then maybe R is getting more complicated. Maybe the region over which you integrate is getting more complicated. Okay, but this is one example. So you see this transformation. This doesn't say how to use the substitution rule for double integrals, but it shows you at least for one transformation you have a feeling how the transformation acts on works on the plane. Okay, so any questions to this? Now, the question which we have to solve is, we haven't solved it yet, is this one here. Okay, so if you do such a substitution in general, what happens with the dA? This is the general question we want to solve. For this, okay, we look at the following. Okay, so let's assume we have given a transformation, C1, of course, which maps the UV plane onto the XY plane. So you have here UV, and here you have XY. So here we have our S. So our S may be, like in the situation which we just saw, maybe a rectangle. Okay, so this is our S. And under the transformation, you get here some region R. Okay, so let's assume that this point here gets mapped onto this point here, and this line here onto this line. Okay, so you have here a point, let's call this U0, V0, and let's assume that this point gets mapped onto this one, X0, Y0, and once more, this line here onto this line. Okay, but this line here is easy to describe. If you prefer vector functions, so let's introduce the vector function R of. So for this one, okay, R of U. R of V. Or let's look at this one first. R of U. Okay, so here we have to fix V. V is equal to V0. The components of the vector functions are those two. Okay, so you have X of U V0 I plus Y of U V0 J. Okay, so this is so this describes here the image of this here. So as U goes from this point to this point, our R of U will go from here to here. Okay. Now the derivative of this vector function, which corresponds to the so if I take the derivative here, okay, with respect to the parameter, what I get is the tangent at this point, and then I evaluate it U0, V0, then I get the tangent at this point here. Okay, so the derivative is equal to the limit. Now, okay, so U tends to U0, and then I have R of U minus R of U0 over U minus U0. What I want to do is I want to call the length here. Let's say the length here is, let's say this region, okay, is a rectangle with a very, very small both sides very, very small. So this delta u, this delta v here. Okay, so this is roughly here, this limit is roughly, I can approximate it by r of u0 plus the delta u minus r of u0 over delta u. Okay, so this tells you from this, if I look at things like this, you see that roughly this vector r of u plus delta u minus r of u0 is roughly the derivative of r with respect to u times delta u. Now, similar, if you, I shouldn't write things like this. Now I have to introduce another. Okay, so let's say another one. Let's say S. Is S a good? This U. U is not a good notation. So let's say T. Okay, so let's say if we introduce another vector function, okay, which is similar to this one, but we fix u, okay, then okay, so we have x u0 v. Now v is the variable, u is fixed. I plus y u0 v j. So what does this function now describe? So now I'm walking here upwards, okay, and what I get here is this one. Okay, and I do the same, so similar. Then you will easily figure out that t v0 plus delta v minus t v0 is roughly the derivative of t with respect to v, okay, times delta v. Okay. Now, what is the meaning of those two? Why I'm interested in those two vectors, in this one and in this one? Because, okay, this vector here is this one. And this vector here is this one. Okay. So this means that because the area here of R roughly is the cross product between those two here, the length of the cross product between those two. Okay, so the area of R is roughly, okay, if I replace this, because I assume that this is very small here, this is also very small, so this will more or less look like a parallelogram. So those two vectors here, okay, if I replace R by the parallelogram which is spanned by those two vectors, the area will be roughly the same. But the area of the parallelogram spanned by those two vectors is given by the absolute value of the vector product between those two vectors. But here I have that they are roughly, the length of this one is this one, roughly, and the length of this one is this one, roughly. Okay, so this will be roughly the length of RU, a vector product with TV times, and then I have delta U, delta V. Okay, so I need this length here. Okay, but this length, you see, if you differentiate this vector with respect to u and then plug in u is equal to u0, what you get is here, in terms of x and y, you just get the partial derivatives with respect to u. Okay, so the length here of this one, so if I look at the cross product, at the vector product, okay, we know by general rule, okay, we can compute this as, okay, so we look at the determinant of the matrix I, here J, here K, then here we have to write the vector, this vector here. But this vector is partial derivative of x with respect to u, partial derivative of y with respect to u, and then here 0. And the last one is the partial derivative, because this one. So here I take the derivative with respect to v. So the partial derivative of x with respect to v, partial derivative of y with respect to v, 0. Okay, and this by the general rule for the determinants, the only one which is, I should write this at the end, is left is the last one. So I get the determinant of and here I have the partial derivative of x with respect to v, and here the partial derivative of y with respect to v times k. Now I wrote things slightly different to our textbook, so I can erase this one. But if you plug this in here, because we have still to take the absolute value here, so this is the determinant, so this times this minus this times this here, okay, and the area of R is roughly, okay, because of the length of this one, okay, so it's the absolute value of this determinant. Okay, so it's the absolute value of the partial derivative of x with respect to u times the partial derivative of y with respect to v minus the partial derivative of y with respect to u times the partial derivative of x with respect to v, and times delta u times delta v. And for this kind of determinant, actually, because this one is this one, we have a special notation. Now, this notation is the so-called Jacobian of this transformation here. Okay, so normally we use this notation here, but normally it doesn't matter because you have here absolute values, but normally this is defined as the determinant. Maybe I should write determinant to make this once clear. If I write this is not a matrix. This is a determinant. Okay, so the determinant of the matrix in our textbook it's defined like this, but it doesn't matter. Looks like different from this one, but because we have here absolute value, it doesn't matter. Okay, so we see that this area here is roughly the Jacobian, the absolute value of the Jacobian of our transformation times delta u times delta v. And if here the delta u and the delta v is very, very small, okay, this will become more and more equality sign. Okay, now we are already almost done in figuring out if you have a general transformation, what will happen with the dA. Namely, if you have now a general, okay, so now we are in the general situation. Let's say you have here uv. Now let's say you have here a very large rectangle. This is our S. Okay, and here we are in the xy plane. And here we have some, so call this here R, and this will, no, I shouldn't write this inside, R, and this here S, and we have our transformation acting here. Now, normally what you have given is, because we want to do a change of variables, so normally what we have given is the double integral over R, not over S, okay, because normally we start in the xy plane. So the double integral over R, and then some function f of x y dA. And what we want to do is we want to use T, our transformation, C1 transformation, okay, in order to replace x and y by u and v. Okay, now, okay, we know that that we can write this integral here. So this will be roughly, okay, so what I do is I into subregions. So actually the way I do this is, okay, I'm not dividing R, I divide S. Okay, I divide S in S, which is a rectangle, into the usual subrectangles. Okay, and then I map this subdivision using T onto R. I will get here something like this here. Okay, it's not really correct, but okay. Okay, so I divide first S into subrectangles, and under T I will get the subdivision of R. Okay. Now our double integral, by definition, okay, will be roughly the sum. Okay, I from 1 to. So maybe I use here here n and here m. Then I have I from 1 to n. I get the corresponding number here for R. So I from 1 to n, j from 1 to m. Then f evaluated at some sample point. Okay, so in every of those subregions, I choose a sample point. So let's say xi j star, yi j star, and then multiplied with the area. So for instance, if this is the Rij subregion, multiplied with the area of Rij. This is actually not our definition of the double integral, because for our definition of the double integral, okay, for a general region, you remember we first defined it for a rectangle and then we extended it to general regions. So this would need some thinking, okay, whether this is really true. Okay, but of course you will believe me that this is true, because as the subdivision is getting smaller and smaller, okay, there should be no difference in the approach we used and this one. Okay, and now we can use our mapping. Okay, so we replace this point here by this sample point which we choose here corresponds to a sample point which we choose here. Okay, and we use our mapping T to replace those two sample points by new sample points in the UV plane. Okay, so we have something like now in the UV plane. Okay, so we have here f of a new sample point uig star and vig star obtained via our transformation. Okay, and if you prefer, sorry, I should write this different. This is x of uij star vij star. And y of, because I apply, of course, my transformation, I have to plug in my transformation, vij star. But for this here, for this area, we have just found this expression here. Okay, so this will become multiplied with the Jacobian of our transformation. Okay, times delta u times delta v, and then you see this will become a double Riemann sum. And as n and m tends to infinity, this will go to a double integral. Okay, so multiplied with the area of the ij's subregion, but this area I can approximate by this one. So this will be times the Jacobian, sorry, x, y, times delta u times delta v. Okay, and as now n and m tends to infinity, this here becomes the double integral now over S, our new region, f of x uv y uv, and then we have here the absolute value of the Jacobian times dA. dA here is now in the UV plane, so maybe let me write it as d u dv. So here you see, okay, what is the effect of the transformation onto dA? This here, the Jacobian. You have to multiply with the Jacobian. Okay, so if we choose x is equal to r times cosine of theta, y is equal to r times sine of theta, the Jacobian should become r. Okay, and then we are in the special case before. So this is the so-called substitution rule for double integrals. And you have a similar result for triple integrals. Of course, you need some assumptions here. You find these assumptions in our textbook, because as you see here, I haven't been very precise in proving this. I say this is roughly this is roughly this, and so on. This is not very precise. Okay, and in particular, it's not really clear which assumptions I need in order to apply something like this. Okay, it seems like 1-to-1 is something which I need. Okay, I certainly need that the transformation is C1. Why do I need that? Because if the transformation is C1, all those guys here are continuous, which means, okay, this here is continuous and the integral exists and so on. Okay, so I need some assumptions. The assumptions normally, which you find in our textbook, is a C1 transformation. The Jacobian is not equal to 0. This is necessary. Then T maps, of course, what you need is that T maps S onto R, and you need that this transformation is 1-to-1. The only exception may be the boundary of S. Okay. Under this assumption, you can prove that this rule is correct. And you have the same. You have the same for triple integrals. So for triple integrals, you have the same. You just define the Jacobian. Okay. You add here. If you have a triple integral, you have x, y, and z, and you change to, let's say, r, s, and t. And then you have here the partial derivative of x with all the 3 coordinates, then y with all the 3 coordinates, z with all the 3 coordinates. So you get here just the difference is just that you get here a 3 times 3 matrix, and you compute the determinant of this matrix, and this is the Jacobian. But the same rule, similar assumptions. Okay, so maybe let's first check whether this really is the same as the rule we found previously when we looked at the special example of polar coordinates. Okay, so if we look at polar coordinates, what we use is this transformation. Okay, so what is the Jacobian? Okay, so the Jacobian is the determinant of the first row is partial derivative of x with all the with respect to the coordinate to the new variables. So with respect to r is the cosine of theta. With respect to theta is minus r times the sine of theta. Then the second row is y with respect to all coordinates. So here you have sine of theta, and here you have r times the cosine of theta. Okay, so you see that the determinant is, okay, you multiply those two, so r times the cosine square of theta plus r times the sine square of theta, which is r. And this explains, okay, why we have to choose r. Okay, so this means for the rule, okay, what we do is, okay, we start in the xy plane. Okay, we have a function and we use this change of this transformation. Okay, and what we have to do is, okay, we have to figure out, okay, which region under this transformation gets mapped onto R. This is S. So this is nothing else but R in polar coordinates. And then we plug in r times cosine of theta, r times sine of theta, and the dA, because of the Jacobian is r. Actually, you have the absolute value of the Jacobian, but r is always positive. Okay, or at least we assume that r is always positive. R can also be negative for polar coordinates, but it depends on the way we want to represent points by polar coordinates. So we have here an r, and then we have dr d theta. Okay, so this is our previous rule. So this our previous what we found previously. So our rule works for polar coordinates. Now let's maybe look at some other examples. So let's look at the following example. So we have given this double integral where R is the region bounded by y squared is equal to 4 minus 4x, y squared is equal to 4 plus 4x, and the x-axis now this example is not complicated. I mean, I don't need a change of variable for this example. The region is not too complicated. The function is not too complicated. Okay, so it just should serve as an example. Okay, so we are in the xy plane, and the region looks like this here. Of course, as I said, of course you do not need a change of variable for such a simple example. Okay, you just integrate over this here, use Fubini, and that's it. But another way to using the transformation rule would be, okay, you observe that the region here is exactly the one which I considered before, which under the map x is equal to, what was it, u square minus v square, and y is equal to 2uv maps the rectangle, the unit rectangle, onto this region here. Okay, so another way to compute this integral would be, okay, first to make this observation. You observe that if you choose this transformation here, then you observe that this rectangle here, the unit rectangle, so where you have here 1, 1, is mapped onto this region here. So meaning that this transformation will make the region over which you integrate much easier. And this might be a motivation for using substitution. But of course, you might say, okay, how does someone come up with such a transformation? This is another topic. This is not so easy. And from last semester, you know, applying substitution rule for integral over a function of one variable, it also needs some practice to figure out the right substitution. Here the same, but here you, since the functions you use for substitution are transformations from the plane into the plane, it's much more complicated. Okay, but if you use this here, okay, so what happens with this integral? Now, the region here becomes much easier. So this is now, our R is now this one. And if we use this substitution, then our, this transformation, then our S is becoming this one. So very easy. The S is becoming very easy. So we just have this double integral. Now the y becomes this function, and we have to figure out what is the Jacobian. Okay, so the Jacobian is, okay, the determinant, the first row you have the partial derivative of x with respect to u, which is 2u, the partial derivative of x with respect to v, which is minus 2v, the partial derivative of y with respect to u, which is 2v, and the partial derivative of y with respect to v, which is 2u. Okay, so this will be 4u squared plus 4v squared. Okay, so this here becomes 4 times u squared plus v squared du dv. Okay, and you can solve this. You see, but I should stress maybe once more that this example you do not need the substitution. But you see here, one possible reason for introducing a substitution is to make the region easier, like in this example. Okay, it's not so easy, and of course it's not so easy to figure out which transformation makes, transformation really makes R easier. Okay, so here for this example it would be not so easy maybe to come up with this transformation. But this is one reason, okay? But you see that the y is getting more, that the function over which you integrate is getting more complicated, not really complicated, but more complicated. Another reason for using substitution is to simplify the function over which you integrate. This would be another reason. So more or less you have those two reasons for applying the substitution rule. Maybe let's look at another example. Since this example is not so convincing, let's look at another one. For instance, this one. So where R is the parallelogram enclosed by x minus 2y is equal to 0, x minus 2y is equal to 4, 3x minus 4 is equal to 1, 3x minus 4 is equal to 8. Okay, so you see you have two lines here. Okay, and two are like this, the other one's like this, so you have a parallelogram, and they have a certain distance from each other. So the first thing, of course, would be plotting the R, but not really necessary here, okay, because you already, wait a moment, maybe I would, no, this is the wrong one, because this would not work. So sorry, so this is 0, this is 2 here, this is 0, and this one, x plus y is equal to 3. Okay, so you see, if you plot this, okay, so this one is x is equal to y. So let's plot this. Or y is equal to x. And this one is y is equal to x minus 2. Okay, so you have like, you are shifted down. Okay, so we have something like this here. Now, this one the other direction. So y is equal to minus x. So like this. And this one is y is equal to minus x plus 3. So shifted like this. Okay, so you really have a parallelogram. This here. Now, from this special form of the example, normally the examples are so easy that it's normally quite clear how to choose the substitution. Because if it is not quite clear, it's always complicated to do substitutions. Now here for this one, you see already the substitution which certainly makes sense is to call this here u and this you call v. Because if you do this, okay, then in the uv plane you have a rectangle. So the rectangle gets mapped onto this parallelogram. This kind of means you just rotate it. Okay. So the substitution you will use is u is equal to x minus y and v is equal to x plus y. Okay. Because then in the uv plane, you see u is equal to 0, u is equal to 2 is the boundary. So and for v, you have between 0 and 3. Okay, so what you get is this rectangle here. So this rectangle under the map gets mapped onto this one. And you see that normally doing substitution doesn't make sense if the function is getting much more complicated. But you see the function is also getting easier. Okay, because this one will be v, and this one u times v. Okay, so the double integral over r x plus y and then e to the x squared minus y squared dA will become, okay, so the u goes from 0 to 2, the v goes from 0 to 3, and then we have v e to the uv, and here we have still to compute the Jacobian. Okay, but the Jacobian is like this here. So we have, from those two, we have first to express x in terms of u and v, and y in terms of u and v. But of course, for this example, it's easy. So x will be equal to u plus v half, and y will be equal to v minus u half. Okay, so you see that the Jacobian becomes the determinant. So this is 1/2. This is the partial derivative of x with respect to v, which is 1/2. The partial derivative of y with respect to u, which is minus 1/2. The partial derivative of y with respect to v, which is 1/2. Okay, so what you get is 1/2. So here you have 1/2, and then you have what is dv du. Okay, and this is not complicated to integrate. Of course, it is better here to interchange, of course, because if you first with respect to v, you need partial integration, but if you interchange those two, you do not need partial integration. Okay, and you can solve this example. So the rest is just computation. But you see how to do the substitution here. Now you also see that here it's quite easy to come up with the substitution. Other examples where it's easy, not so complicated to come up with a good substitution is the following one. For instance, the double integral over the ellipse of sine you see the idea should be pretty clear. What do you, which kind of substitutions do you suggest here? Any suggestions? Any ideas? So you wanna, because the ellipse is more complicated than the circle. So the idea is you just find a substitution which will transform the ellipse into the circle. Okay. So for this, you see from here already that you will the u will become 3x, and the v will become 2y. Okay. If you do this, then you see that just plugging in here u squared plus v squared will be smaller or equal than 1. And you integrate over the circle instead of integrating over the ellipse. Okay, so this will become the double integral u squared plus v squared is smaller or equal than 1. And then you have here the sign. And we have to plug in here our substitution. So we have here u squared plus v squared. And we have still to figure out, okay, what happens here. So for this, we have to compute the Jacobian. Okay, the determinant. So here the partial derivative of x with respect to u, which is 1/3, with respect to v, which is 0. Here the partial derivative of y with respect to u, which is 0. And here we have 1/2. So what you get is 1/6. So you see, here you have a 1/6. And here you have du, dv. And now, once more substituting polar coordinates. Okay, or at the beginning you already substitute. Another possibility would be the second method. You choose from the beginning u is equal to 3 times r times the cosine of theta, and v is equal to 2 times r times sine of theta. Okay, this would be another way. So you combine first replacing the ellipse by a circle and then going on with polar coordinates. And you see that the integral here becomes then very easy with polar coordinates because you go here over the circle. So the r goes from 0 to 1, the theta goes from 0 to 2 pi. You have here sine of r squared, and fortunately you have another r. Okay, and then dr d theta, and this is easy to compute. I'm not going to do this. Okay, so you see here another example. Ellipse, if you have to integrate over ellipse, you can use the substitution, this kind of substitution to replace the ellipse by a much more easier region, namely the circle. Now, maybe for a triple integral, okay, let's maybe write down the rule for the triple integral. So you have a similar rule. But the transformation is getting now much more complicated because x is equal to x r s t, y is equal to y r s t, z is equal to z r s t. And if you do the substitution, you have to figure out first, okay, under this transformation, here you, from the xy plane, from the xy space, xyz space, the other way around, sorry, from the RST space into the XYZ space, okay, which region under this transformation gets mapped onto the space region R? So we have to figure out here S, which normally is quite complicated. And but the rest is, okay, you just plug this in here. So you have x of R of S of t, y of R of S of t, and the set of R of S of t. And then here you have, again, the absolute value of the Jacobian. Multiplied with dr dsdt. So this is the effect onto dA. Okay, where the Jacobian is defined similarly just by a larger, no, sorry, this is x with respect to s. This is the partial derivative of x with respect to t, the partial derivative of y with respect to r, the partial derivative of y with respect to s, the partial derivative of y with respect to t, the partial derivative of z with respect to r, the partial derivative of z with respect to s, the partial derivative of z with respect to t. But of course, to come up, for many examples, come up with a clever substitution to simplify a given triple integral, not so easy, okay? And you can do the same for a general integral, okay, which is over a function of n variables. And then it's even more complicated to come up with a tricky substitution in general, okay? Because here, at least, the region over which you integrate, you can visualize it. But if you go to the four-dimensional space, even the region, you cannot easily visualize it. And it's not clear which region in the four-dimensional space is makes things much more easier and so on, which transformations. And it can be quite complicated in general. Okay, so maybe let's use this to check, because last time we talked about spherical coordinates, and with spherical coordinates, if we go from rectangular coordinates to spherical coordinates, this guy here becomes rho squared times the sine of psi. So let's check whether this fits into this setting. So in other words, we do the substitution. X is equal to rho times sine of psi times cosine of theta. Y is equal to rho times sine of psi times sine of theta. And z is equal to rho times the cosine of psi. So this is our transformation, okay, going from rectangular coordinates to spherical coordinates. So the only thing I have to compute is the Jacobian. So what is the Jacobian? Rho and let's the second one. It doesn't matter. Let's say theta. You see, you have a free choice here of the order, okay? Because here I say R, S, and T, but of course you can rename those two. This doesn't affect here the result because here you have an absolute value Okay, you know maybe already from linear algebra if you have a determinant and you switch two of the columns. Okay, the only thing which changes is minus. Okay, but for the absolute value it doesn't matter. So it doesn't matter which one. Of course, it should be like this. Okay, it doesn't matter which one of the variables, okay, comes first. Okay, so for this one, so I have the determinant. Now x with respect to rho. So we have here sine of psi, the cosine of theta. Then x with respect to theta. So we have here minus sine of psi, sine of theta. And x with respect to psi. So we have here rho times cosine of psi times cosine of theta. Okay, so this is the first row. Now the second one. Okay, so here we have sine of psi, sine of theta. Now with respect to theta, so we have rho sine of psi, cosine of theta. And here with respect to theta, so we have rho times cosine of psi, sine of theta. And the last one is with respect to rho, so we have cosine of psi with respect to theta, which gives us 0. And here with respect to psi, which gives us minus rho times sine of psi. And this determinant. Now, I guess you have encountered determinants in linear algebra, so you know how to compute determinants. There are different ways for something like this. You know, one of the rules is Lagrange rule for computing determinants. For Lagrange rule, normally you choose the row which has many zeros. So this one is better than this one. Okay, so we are going to choose this one. Okay, so if we use Lagrange theorem to compute here the determinant by using this row here, what we have is, so we have for the first one cosine of psi, and then we have to delete this column, this row here, so and then the determinant of the submatrix which we get, which is then minus rho times sine of psi times cosine of theta. Here we have rho times cosine of psi times cosine of theta, and here you have rho times sine of psi cosine of theta, and here you have rho times cosine of psi sine of theta. Okay, so this is this part. So this was for this element. Now for this element here, nothing because of 0. And for this element, we have minus rho times sine of psi multiplied with the determinant of the submatrix you get if you erase this row and this column here. You have learned this rule, right, in linear algebra? Yeah, okay. Then here, or if you don't know, if you forgot this rule, then just switch rows. It's the same, because our definition, which I gave, I don't know, last semester or at the beginning of this semester, was using this here, this row. Okay, but here we have the sine of psi, the cosine of theta, minus rho times the sine of psi, the sine of theta, and here sine of psi, sine of theta, and here rho times sine of psi, cosine of theta. Okay. So there's still some terms which we have to consider. So this we have to compute this determinant here. So what do we get? We have cosine of psi. Now times. So the determinant of this one. So this multiplied by this one. Okay, let's write everything out. Minus rho square sine psi cosine psi sine theta cosine theta minus, and here we have rho square, and then we have again we have sine psi cosine psi which means there is a mistake, which means this must be this must be sine. Okay. This is cosine, this is cosine, this is sine. I'm doing this computation every year and every year mistake. So let's maybe, because sine, cosine, you get mixed up with all those functions. Okay, so so also this year a mistake. So maybe next year I will be more successful. Okay, so minus rho times sine of psi. And what? So what do we have here? Actually, we could simplify this, but let's maybe do it slowly. Rho times sine of psi square, and then we have cosine of theta square, and then we have plus, and we have here rho times, and then we have again sine of psi square and the sine of theta square. Okay, which is good because many things simplify. Okay, so I erase this here. Okay, so here we can simplify, because this plus this is equal to 1 and the rest is the same. So we have here minus rho times sine of psi cosine square of psi minus, and then rho times sine of psi. And you see, here we can also take out rho times sine square of psi, and the rest is equal to 1. So we have here a rho square, and we have here to the cube. Okay, which is good because we can take out, here we have a rho square. Now, which is good because we can take out minus rho square sine of psi, and the rest is equal to 1. Okay, and you see, what we get is this one. Minus, okay, but this doesn't matter because we have the absolute value. Okay, so the absolute value of this is rho square times sine of, you have to notice that sine of psi is always positive because psi is between 0 and pi, where the sign is positive. So this is really negative here. Okay, and the absolute value makes it positive. So you can, I mean, because of the absolute value, you can drop here the minus. Okay, it's not that depending on psi, it's sometimes positive, sometimes negative, because psi is between 0 and pi. So you get here really, for changing from rectangular coordinates to spherical coordinates, you really get here a factor which is rho square times sine of psi. And actually, this is the rule we already established last time. So everything fits together. Okay, so any questions to this? You find some more examples for doing the substitution rule in our textbook, but most of those examples which we find in our textbook are either they tell you already what is the substitution, or the substitution is so easy to see from the example that you do not even have to think more than 1 second to find it. So because the reason for this is because the general situation, okay, where you have a general integral and you really have to figure out the substitution to make it really easy can be very tricky sometimes. This is actually no real surprise because now we are used to it using the substitution rule for a normal integral over a function of one variable. But also for this situation, last semester we had to do some training to figure out, to learn how to find out the right transformation or the right substitution. It's the same problem you have here. But here the real problem is that for a triple integral, the substitution is from the space. The function you have to choose is from space into space, and we are not so used to such functions. And this makes it complicated in many cases to find the right to find a good substitution to really simplify a triple integral. Okay, so any questions to this? Now, as I said, this actually finishes what I have to teach in this course. I mean, what you have to know for the Hui Kao. But of course, this is not the end of calculus. This is just the beginning. And there are much more topics which are important for your further studies. Now, one topic which we, because of time, normally cannot cover is chapter 16, and this week and next week on Monday I will spend some time introducing some of the main things from chapter 16, something which you have certainly already seen in other classes and which you will need in particular if you study something which is related to engineering or physics. The chapter 16 discusses so-called vector fields. Okay, so first the definition of a vector field. Okay, so we choose or let D be a region in the plane, then a function from D into the two-dimensional vector space. So into this is what we call V2. It's called a vector field. Or more precisely, a two-dimensional vector field. Okay, so a vector field is just a function which maps some plane region into, which maps every point in a plane region onto a vector. Now, normally we use this notation because such vector fields are important in, for instance, physics. Normally appear as force fields. So that's why we call a vector field quite often. We use this notation in order to denote the vector field. Okay. And so this means that the image of this point here is a vector. Normally we use for the component functions, okay, we use p of xy, and here q, another function q of xy. Okay, and these two functions normally are called the scalar fields or component fields. Now we have the same definition, so you can think about the vector field as okay, in the plane, if D is equal to the whole plane, for every point in the plane you have attached a vector which tells you, for instance, at this point what is the force at this point. Now you have the same definition. So this is a two-dimensional vector field, and you have similar for a three-dimensional vector field. Okay, where you so similar in the space, so three-dimensional vector field. Okay, so you have then a function of three variables, and here for the component functions or the scalar fields you have three functions. So one is p x y z, the other one is q x y z, and the last one r of x y z j. You know, one of those examples, certainly from physics, is the so-called gravitational field, which attaches to every point. So you can assume like the Earth is in the origin of the coordinate system, and for every point x in the space, you have a force attached to it, which is the gravitational force. And the gravitational force, of course, is directed to the center of the Earth. So the gravitational field normally is described by Newton's law of gravitation. So this is the gravitational field. So a three-dimensional vector field where to okay, every point in the space, okay, you have attached a vector which points to the origin of the coordinate system. This is what you see here, because I should say what the x is. The x is the position vector given by those here, x, y, and z. Okay, so you have for every point in the space you have attached a vector. So for instance, for this one, which as direction has the negative direction of the position vector, okay, so points to the origin of the coordinate system, and has length given by this here. Normally, if you have a three-dimensional vector field, I guess I don't have to explain this. This is the masses of the two objects. So this is the mass. One of them is the mass of the object you place in the origin. The other one is the mass of this object here, and g is the gravitational constant. Now, you see already for this example that normally it's not so easy to depict a three-dimensional vector field. Also two-dimensional vector field, not so easy to depict. But graphing devices like Maple have functions, have plotting functions for such vector fields. So you can give Maple such a vector field and tell Maple plot it, and Maple will give you a plot of the vector field. So Maple will attach to every point a small vector which tells you the direction. And normally, because the length here is normally given by the vector field, and if vectors are too long, okay, Maple will suitably scale them such that the relative length to other vectors is preserved, and that you get a good picture of the vector field. Now, you know maybe a notation from physics which is so-called conservative vector fields. So actually we have learned already, we have discussed already one example for a vector field, the so-called gradient field, okay, where you have given a function of two variables and you look at the gradient attached to every point in the plane. This is a special example for a vector field, so the gradient field. Okay, so we have given a function, let's say, of 3 variables. Okay, and we look at the vector field, which is given by the gradient. Okay. So the partial derivative of f with respect to x times I plus the partial derivative of f with respect to y times j plus the partial derivative of f with respect to z times k. So this is the so-called gradient field, so a special three-dimensional vector field for a given function. And you know that this special vector field has some certain properties, like if you make a plot of this vector field and you also plot the surface the level surfaces of this function, okay, then for every point on the level surface, okay, the attached vector will be perpendicular to the level surface and will point into the direction of fastest increase. Okay, so this gives you, of course, many examples for three-dimensional vector fields. Now, if a given three-dimensional vector field, okay, if for a given three-dimensional vector field there exists the function f such that the vector field is can be described as a gradient vector field, such a vector field is called conservative vector field, and those vector fields frequently appear in physics. Conservative vector field f. So there exists f, which is normally called potential function, such that f can be described as a gradient vector field. Okay, then the f is called potential function. And many of those vector fields encountered in physics are actually conservative. Okay, so for instance, this one is one example for a conservative vector field. What is the potential function? you can easily figure out that you can write this where f is equal to m times g over the square root of x squared plus y squared plus z squared. Okay, so 1/2. No, it's correct. Okay, so this the gravitational vector field is an example of a conservative vector field, and if you check many of the examples you encounter in physics, actually there are many who are conservative vector fields. So one of the main questions which is answered in section 16 is okay, how can I see that the given three-dimensional vector field is conservative? How can I find the potential function? Okay, so we have kind of in chapter 16 you will have a couple of theorems which tell you under which conditions three-dimensional vector field has to satisfy such that it is conservative. This is one of the main issues of chapter 16. The other one is extensions of the fundamental theorem of calculus to double and triple integrals. So this is more a question which is interesting from a mathematical point of view. So for instance, for a double integral, do you have something similar to the fundamental theorem of calculus? This is, from a mathematical point of view, an interesting question. This question here, given a three-dimensional vector field, how to see that such a vector field is a conservative vector field is more interesting from an application point of view. Okay, so on Thursday I will spend some time answering this question. Okay, so any questions? If not, then we make a break of 5 minutes. You will get back your English homework and your assignment, your homework paper from last week. And after the break, we will spend a little bit time discussing the examples from last week.